The outer solar system is not behaving the way it should. Beyond Neptune, distant, icy objects follow the same strange orbital pattern. They're aligned, organized, controlled. This shouldn't happen in a stable solar system. The math says something massive is pulling on them, something we haven't found. And that's why astronomers believe something is disturbing the outer solar system. The story begins in 2003 with the discovery of an object called Sedna. Sedna is a small world, perhaps 1,000 kilometers across, orbiting in the extreme outer reaches of the solar system. When astronomers first plotted its orbit, they realized something was deeply unusual about it. Sedna's closest approach to the Sun is 76 astronomical units away. 1 astronomical unit is the distance between Earth and the Sun, about 150 million kilometers. So Sedna, at its nearest point, is 76 times farther from the Sun than we are. That might not sound immediately strange. After all, we know there are objects out beyond Neptune. The Kuiper Belt is full of them. But here's the problem. Everything in the outer solar system is controlled by Neptune's gravity. Neptune is the gravitational sheriff of that region. It kicks objects around, pulls them into resonances, shapes their orbits. If you want to understand why something is moving the way it is out there, you start by looking at Neptune. But Sedna never comes anywhere near Neptune. At 76 astronomical units, Sedna is completely isolated from Neptune's gravitational influence. Neptune orbits at 30 astronomical units. It can affect objects that cross its path or come close to it, but Sedna stays far away, always. So how did Sedna get into that orbit? At the time, astronomers didn't have a good answer. Some suggested that maybe a passing star had disturbed it billions of years ago when the Sun was still part of its birth cluster. Others thought it might be a relic from the solar system's chaotic early days, when planets were migrating and scattering objects in all directions. But these were just guesses. Sedna was alone, a single oddball. Interesting, but not enough to build a pattern. Then, nearly a decade later, astronomers found another one. In 2012, astronomers discovered an object called 2012 VP 113. Like Sedna, this object had an extremely distant perihelion, the point in its orbit where it comes closest to the Sunday. In this case, the perihelion was 80 astronomical units, even farther than Sedna. And like Sedna, 2012 VP 113 never interacts with Neptune. It's too far out. Its orbit keeps it in a region of space that Neptune's gravity simply doesn't reach. Two objects with similar characteristics, both isolated from the giant planets, both on highly elliptical orbits that take them far beyond the known architecture of the solar system. That got people's attention. In 2014, astronomers Chad Trujillo and Scott Shepard published a detailed analysis of these distant objects. They had been searching for more of them, and by then, they had identified a small population. What they found was striking. These objects weren't just far away. Their orbits seemed to be pointing in the same direction. To understand what that means, imagine looking down at the solar system from above. The planets all orbit in roughly the same plane, like a flat disk. But each planet's orbit is oriented slightly differently. Some are tilted a bit. Some are rotated. The orientations are essentially random. Now look at these distant objects. Their perihelia, the points where they come closest to the Sun, are all clustered in one region of space. Their orbits aren't randomly oriented. They're aligned. Statistically, that shouldn't happen. If you scatter a bunch of objects randomly around the Sun, their orbits should point in all different directions. There's no reason for them to line up, unless something is organizing them. Trujillo and Shepard suggested that the alignment might be caused by the gravitational influence of a large, distant object, something massive enough to shepherd these smaller bodies into similar orbits over billions of years. This was the first formal suggestion that something undiscovered might be out there, shaping the outer solar system. But the evidence was limited. Only a handful of objects, lots of uncertainty. The idea was intriguing, but far from proven. Then, in 2016, two astronomers at Caltech took the analysis much further. Konstantin, Batygin, and Mike Brown were studying the same population of distant objects. They focused on the 6 most extreme cases: objects with perihelia beyond 30 astronomical units and semi-major axes beyond 250 astronomical units. What they found was more than just alignment. The orbits of these 6 objects were clustered in 3-dimensional space, not just in the direction they pointed, but in the way they were tilted. All 6 orbits were inclined about 30 degrees downward relative to the plane of the solar system. And their arguments of perihelion, the technical term for the orientation of their closest approach, were also aligned. This is extraordinarily unlikely. The orbits of these objects move around the solar system at different rates. They precess slowly, like the hands of a clock, all moving at different speeds. The odds of catching all 6 pointing in the same direction at the same time, purely by chance, are about 0.007%. Batygin and Brown ran computer simulations to test different scenarios. Could this be random? No, the probability was too low. Could it be caused by observational bias? No, the alignment persisted even after accounting for where and when astronomers were looking. Could it be the result of interactions with Neptune? No, these objects are too far away. The only scenario that consistently reproduced the observed pattern was the presence of a massive perturber, something with significant gravity, orbiting far beyond Neptune, gently nudging these smaller objects into aligned configurations. But here's where it gets interesting. The simulations didn't just explain the clustering, they predicted something else. If a massive object was shaping these orbits, it should also be creating a second population of objects on highly inclined orbits, nearly perpendicular to the plane of the solar system. And when Batygin and Brown looked at the data, they found exactly that. 5 objects had already been discovered on steep, perpendicular orbits. The simulations matched the observations. This is what made the hypothesis compelling. It wasn't just explaining one anomaly. It was explaining multiple independent features of the outer solar system that no one had connected before. But what could be causing this? Before we talk about what the disturbing object might be, let's talk about what it would need to do. The gravitational signature suggests something very specific. The disturber would need to, first, maintain long-term stability. These orbits have been aligned for millions, possibly billions of years. Whatever is causing the alignment has to do so without ejecting the objects from the solar system entirely. Second, create anti-aligned orbits. The simulations show that the most stable configuration happens when the perturber's orbit is oriented opposite to the orbits of the smaller objects. When their perihelia point in one direction, the perturber's perihelion points in the other. Third, protect through resonance. The objects need to be locked in mean motion resonances with the perturber. This means that for every few orbits the perturber completes, the smaller objects complete a different number of orbits, and the timing keeps them synchronized. They never get close enough to collide. Fourth, generate perpendicular orbits. The same gravitational interactions that cluster some orbits should flip others into steep inclinations. This is a natural consequence of the dynamics involved. So we're not looking for just any massive object. We're looking for something on a specific type of orbit, with a specific mass range, at a specific distance, exerting a specific type of influence. Now let's talk about what could do this. The first alternative explanation is that the disturbance isn't caused by a single object at all, but by the collective gravity of many smaller ones. Imagine a massive disk of icy debris far beyond Neptune. This disk would contain millions of small bodies, each one individually insignificant. But together, their combined mass could be substantial, perhaps several times the mass of Earth. Each small body exerts a tiny gravitational pull, but if you add them all up, the cumulative effect could be significant. Over hundreds of millions of years, the disk could gravitationally sculpt the orbits of the objects we see, aligning them through a process called collective gravity. This idea was proposed by researchers like Anne-Marie Madigan and Antranik Sefilian. They ran simulations showing that under certain conditions, a massive disk could produce the same orbital clustering that we observe. The advantage of this model is that it doesn't require an undiscovered planet. The disk would be made of material that we already know exists in the outer solar system. It's just a question of how much of it there is and how it's distributed. The disadvantage is stability. A disk like this would need to survive for billions of years without being dispersed. But the outer solar system isn't isolated. Stars pass nearby. The galactic tide exerts subtle forces. Over time, these perturbations would likely scatter the disk, destroying its coherence. Simulations that include these external influences show that the disk model struggles to maintain the alignment over the age of the solar system. It works in idealized conditions, but when you add the messiness of reality, it becomes less convincing. Still, it's a viable alternative, and it's one that astronomers continue to investigate. The second alternative is more fundamental. Maybe the clustering isn't real at all. This is the argument put forward by several independent surveys, most notably the Outer Solar System Origins Survey, or OSOS. Between 2013 and 2017, OSSOS used the Canada-France-Hawaii telescope to search for distant objects. They discovered over 800 trans-Neptunian objects and carefully documented every bias in their observations. Where they looked, when they looked, what they could see and what they couldn't. When they analyzed their data, focusing specifically on the most distant objects, they found no clustering. 8 objects in their survey had semi-major axes greater than 150 astronomical units, making them part of the same population that others were using to infer the disturbance. But these 8 objects had orbits that were scattered in all different directions. No alignment, no pattern. Samantha Lawler, one of the astronomers working on OSOS, argues that the clustering seen in earlier studies might simply reflect where astronomers happened to be looking. Most surveys don't observe the entire sky uniformly. They focus on certain regions, and they observe at specific times of the year. If you only look in one direction, you'll only find objects in that direction. The Dark Energy Survey came to a similar conclusion. They discovered 316 new trans-Neptunian objects and found no evidence of clustering after accounting for observational bias. The skeptics point out that even with recent discoveries, the total number of extreme trans-Neptunian objects is still small, maybe 15 to 20, depending on how you define the population. Small number statistics can be misleading. A pattern that looks significant with a handful of objects might disappear as more are discovered. So maybe the disturbance is an illusion, a trick of incomplete data. But the proponents of the disturbance hypothesis argue otherwise. In 2021, Batygin and Brown published a new analysis that accounted for observational biases more carefully than ever before. They modeled exactly where and when astronomers had been searching, and they asked, if the orbits were randomly distributed, what would we expect to see given the limitations of our surveys? The answer was clear. Even after accounting for every possible bias, the clustering remained statistically significant. The probability that the observed pattern was random was only 0.4%. That's a confidence level of 99.6%. The debate isn't settled, but the case for a real disturbance is stronger than the case against it. There's a third alternative that's more exotic. What if the problem isn't that we're missing an object, but that we're misunderstanding gravity itself? In 2023, a study showed that a modified theory of gravity called MOND, which stands for Modified Newtonian Dynamics, could explain the orbital clustering without requiring a massive perturber at all. MOND was originally proposed to explain the rotation curves of galaxies without invoking dark matter. The idea is that gravity doesn't behave quite the way Newton described it at very large distances or very low accelerations. Instead of falling off predictably, gravity remains slightly stronger than expected. If MOND is correct, then objects in the outer solar system might be feeling a subtle gravitational influence from the Milky Way galaxy itself. This influence would be too weak to notice in the inner solar system, but at hundreds of astronomical units from the Sun, it could become significant enough to align orbits. The study showed that MOND predicts the major axes of distant objects should align with the direction toward the galactic center. And when they checked the data, that's what they found. This is a fascinating possibility. If true, it would mean that the disturbance in the outer solar system is actually evidence for new physics. A hint that our understanding of gravity needs revision. But most astronomers are skeptical. MOND has struggled to explain other phenomena that dark matter handles easily, and applying it to the outer solar system requires assumptions that aren't well tested. Still, it's on the table. And it reminds us that sometimes the simplest explanation isn't the right one. Now let's talk about the explanation that has gained the most traction. Of all the possibilities we've discussed, one keeps matching the data better than the others. The idea that a massive planet, orbiting far beyond Neptune, is gravitationally shaping the outer solar system. The simulations that Batygin and Brown ran in 2016 showed that a planet with about 5 to 10 times the mass of Earth, orbiting at a distance of several hundred astronomical units, could naturally produce all the observed features: the clustering, the perpendicular orbits, the long-term stability. What would such a planet look like? It would be a sub-Neptune, a type of world larger than Earth but smaller than Neptune. These planets are extremely common around other stars. Nearly every planetary system we've studied contains at least one, but our solar system doesn't have one, or at least we thought it didn't. The planet would have a core of rock and ice, surrounded by a thick envelope of hydrogen and helium. It would be cold, with a surface temperature around 47 Kelvin. That's negative 226 degrees Celsius. At that temperature, the planet would glow faintly in infrared light from the leftover heat of its formation, but it would reflect very little sunlight. Its orbit would be highly eccentric, meaning it would swing close to the Sun at one point and drift far away at another. The closest approach would be around 200 to 300 astronomical units. The farthest point could be over 1,000 astronomical units, and it would take between 10,000 and 20,000 years to complete a single orbit. This planet wouldn't interact with the inner planets at all. It's too far away. But it would dominate the gravitational landscape of the outer solar system, slowly shaping the orbits of smaller bodies over millions of years. Here's what makes this explanation compelling. It's not just consistent with the clustering. It predicts other features that we've already observed but didn't know how to explain, like the existence of objects such as Sedna, which sit in a gravitational no-man's land beyond Neptune's influence. The planet hypothesis naturally produces objects like this by slowly pulling them outward from the Kuiper Belt, like the highly inclined objects on nearly perpendicular orbits. The same resonances that cluster some orbits should flip others into steep inclinations. Like the population of retrograde objects, bodies that orbit the Sun in the opposite direction from the planets. The planet's gravitational influence could scatter objects into these unusual paths. Every time astronomers test the planet hypothesis against new data, it holds up. That doesn't mean it's proven, but it does mean it's the leading explanation. Since 2016, astronomers have continued searching for more distant objects, and they've found them. In 2015, astronomers discovered an object nicknamed the Goblin. Its official designation is 2015 TG 387. The Goblin's perihelion is 65 astronomical units, and its orbit is aligned with the others. Another piece of the pattern. In 2018, they found far out, also known as 2018 VG18. At the time of its discovery, it was the most distant object ever observed in the solar system, located about 120 astronomical units from the Sunday. A few years later, they found far out, which was even more distant. These objects pushed the boundaries of what we could detect and added more data points to the puzzle. Then, in 2023, came one of the most interesting discoveries yet. An object called 2023 KQ14, nicknamed Ammonite, was found by a survey using the Subaru telescope. Ammonite has a perihelion of about 66 astronomical units and a semi-major axis of around 252 astronomical units. It's the third Sedna-like object discovered so far. But here's what makes Ammonite unusual. Unlike Sedna and the other objects, Ammonite's orbit is not aligned with the cluster. Its longitude of perihelion points in the opposite direction. It's an anti-cluster object. This is actually important, because if every distant object we found supported the same pattern, you might start to worry that we were only finding the objects that fit our expectations. But Ammonite shows that the population is more complex than a simple clustering. Simulations that include Ammonite suggest something interesting. About 4.2 billion years ago, the longitudes of perihelion of the four known Sedna-like objects may have been tightly clustered. Then, over billions of years, they slowly drifted apart due to the differential precession caused by the giant planets. This hints at a primordial event, something that happened early in the solar system's history that elevated the perihelia of these objects and set them on their current paths. Then, over time, the clustering dispersed. If this is true, it suggests that the disturbance isn't just active today. It's been shaping the outer solar system for billions of years. Let's talk about numbers. In 2016, when the disturbance hypothesis was first proposed, it was based on 6 objects. That's a small sample. And with small samples, you have to be careful about drawing conclusions. But by 2019, the sample had grown to 14 objects. And by 2021, it was 17. Each time new objects were discovered, astronomers recalculated the statistical significance of the clustering. And each time, the clustering persisted. In the most recent analysis, published in 2021, Batygin and Brown calculated the probability that the observed pattern could arise by chance. They accounted for observational biases, the geometry of the orbits, the precession rates, and the limitations of the surveys that found these objects. The result was a confidence level of 99.6%. That means there's only a 0.4% chance that the clustering is a random fluke. In scientific terms, that's significant. Not definitive, but significant. Compare this to the threshold used in particle physics, where a discovery is only considered confirmed if the confidence level exceeds 99.9999% or 5 sigma. By that standard, the disturbance hypothesis hasn't reached the level of proof. But in astronomy, where systems are messy and data is sparse, a confidence level of 99.6% is taken seriously. Of course, statistics can be misleading. If you look at enough different correlations, you'll eventually find something that looks significant. This is why astronomers are cautious. They want more data, more objects, more tests. And that's exactly what's happening. In 2025, a new study analyzed 51 extreme trans-Neptunian objects using updated simulations. They found that the clustering remains, and they refined the estimates for what might be causing it. The statistical case is getting stronger, but the debate is far from over. Not everyone is convinced. The surveys that found no clustering, like OSO's and the Dark Energy Survey, argue that the sample size is still too small and the biases too difficult to account for. Samantha Lawler points out that the objects used to infer the disturbance were all discovered by surveys that focused on specific regions of the sky. These surveys didn't cover the entire sky uniformly. They looked where it was convenient to look, where the weather was good, where the Milky Way wasn't blocking the view. If you only search in certain directions, you'll only find objects in those directions. That doesn't mean the objects are clustered everywhere. It just means you're seeing the result of your search strategy. Lawler argues that when you account for these biases properly, the clustering could easily be a statistical artifact. The pattern might disappear as more surveys with better coverage discover more objects. Another criticism is that different studies use different definitions of what counts as an extreme trans-Neptunian object. Some include objects with perihelia above 30 astronomical units. Others use 40. Some require semi-major axes above 150 astronomical units. Others use 250. These cutoffs are somewhat arbitrary, and depending on which objects you include, the clustering can look stronger or weaker. Then there's the issue of orbital uncertainties. Many of these objects have only been observed for a few years. Their orbits aren't perfectly known. Small errors in the measurements can shift their calculated orbital parameters, which could affect whether they appear to be clustered or not. The skeptics also point to alternative explanations that don't require a massive planet. The collective gravity model, the temporary clustering model, the modified gravity model. Each of these has strengths and weaknesses, but they remind us that the planet hypothesis isn't the only possibility. And yet, despite all these criticisms, the disturbance hypothesis keeps holding up. New surveys are being planned, better telescopes are being built, more data is coming, and within the next few years, we'll have a much clearer picture of whether the clustering is real. Even if we accept that the disturbance is real, there are still many unanswered questions. First, why do some objects fit the pattern and others don't? Ammonite is anti-clustered. Other objects have perihelia that don't align. If a massive planet is shepherding these orbits, why doesn't it affect all of them equally? The answer might be that the population is more complex than we realize. Maybe some objects are in stable resonances, while others are passing through the region temporarily. Maybe some formed in place, while others were scattered outward from the Kuiper Belt. Second, is the clustering primordial or recent? The simulations suggest that the Sedna-like objects might have been tightly clustered 4.2 billion years ago. If that's true, it implies that whatever caused the disturbance acted early in the solar system's history. But we don't know what that event was. Maybe the giant planets migrated outward during the first few 100 million years, scattering objects as they went. Maybe a passing star perturbed the outer solar system. Maybe a massive planet was ejected from the inner solar system and ended up in a distant orbit. Each of these scenarios is plausible, but we don't have enough data to distinguish between them. Third, could multiple mechanisms be at work? Maybe the disturbance isn't caused by a single object or process. Maybe it's the result of several things happening at once. A planet plus a disk, a primordial event plus ongoing galactic tide. A combination of factors that together produce the pattern we see. This is often how nature works. Simple explanations are appealing, but reality is usually messier. Fourth, what happened 4.2 billion years ago? If the clustering was tighter in the past, something must have caused it. The giant planet instability is one possibility. This is a period in the early solar system when Jupiter, Saturn, Uranus, and Neptune were jostling for position, migrating through the disk of leftover material and scattering smaller bodies. Simulations show that during this chaotic period, objects could be kicked into distant, eccentric orbits. If the timing was right, they could have been captured in the configuration we see today. But this is speculative. We don't have direct evidence of what happened back then. We can only infer it from the patterns we observe now. For now, the mystery remains unsolved. But the tools we use to study the outer solar system are getting better. In 2025, the Vera C. Rubin Observatory in Chile began operations. This telescope has an 8.4-meter mirror and the largest camera ever built for astronomy. It will photograph the entire southern sky every few nights for a decade. The Rubin Observatory will discover tens of thousands of new trans-Neptunian objects. If the clustering is real, it will be confirmed beyond any doubt. If it's an artifact of observational bias, that will become clear too. The telescope will also search directly for any massive objects in the outer solar system. Even something as faint as a distant planet should be detectable if it's moving slowly across the sky. Other instruments are helping as well. The James Webb Space Telescope, with its sensitivity to infrared light, can detect the faint thermal glow of cold objects. Radio telescopes can track the subtle motion of distant bodies. Citizen science projects are recruiting volunteers to help search through archival data. The search is comprehensive, methodical, and patient. You might wonder why astronomers care so much about a few distant objects on strange orbits. The answer is that these objects are messengers. They carry information about the history of the solar system, about how planets form and migrate, about what conditions were like billions of years ago. If a massive planet exists beyond Neptune, it would tell us something profound. It would suggest that our solar system is more violent and chaotic than we realized. That planets can be thrown into distant orbits and survive there for billions of years. That the architecture we see today is just a snapshot of a system that's been evolving for eons. It would also make our solar system more similar to others. Surveys of planets around other stars have found that sub-Neptunes are incredibly common. Nearly every star has at least one, but we don't, or at least we thought we didn't. Finding one in our own system would close that gap, and it would remind us that we still don't fully understand our own cosmic neighborhood. We've mapped the surfaces of other planets. We've sent probes to the outer reaches of the system. We've detected thousands of planets around other stars, but we still haven't finished exploring our own backyard. There are mysteries here, waiting to be uncovered. So where does that leave us? We have a pattern, a collection of distant, icy worlds moving in ways that seem to require an explanation beyond the 8 known planets. We have multiple hypotheses. A massive planet, a disk of debris, modified gravity, observational bias, each with strengths and weaknesses. We have predictions, specific characteristics for what might be causing the disturbance, ranges for its mass, orbit, and influence, and we have a search. Telescopes scanning the sky, looking for clues, but we don't have confirmation. Not yet. The evidence is compelling, but not conclusive. The clustering is statistically significant, but small sample sizes can be misleading. The simulations match the observations, but simulations are only as good as the assumptions they're built on. So we wait, and we watch, and we keep looking, because this is how science works. You notice something strange. You come up with hypotheses. You test them. You refine them. You gather more data. And you accept that sometimes the answer takes longer to arrive than you'd like. Whatever is disturbing the outer solar system, it's been doing so for billions of years. It's patient, persistent, and for now, it remains hidden. But the mystery is driving us forward, pushing us to look deeper, to build better instruments, to ask harder questions. And that's the real value of a mystery like this. Not the answer, but the journey toward finding it. The outer solar system is vast, cold, dark, and full of secrets. Something is out there, shaping the orbits of worlds we're only beginning to discover. The disturbance is real. The cause is still debated. And every new piece of data adds another layer to the puzzle. For now, all we can do is keep searching, keep questioning, keep watching the edge of our solar system for signs of what might be hiding just beyond our view. The answer is coming. We just don't know when.